So welcome to my dear student. So this is a requested video. Some of my students, they asked me to explain about the basics of centrifuge. So this maybe some 8 or 10 years back I worked for a company. They were designing the centrifuge, so I have done some simulation and all. So that is different thing, some higher end of the centrifuge design, but still I will explain the very basic of it. And I have added one more things with this, that is the processing of a nuclear fuel. So and to process the nuclear fuel, mainly the uranium, which is the fissile material, so the centrifuge is very important component which is used to enrich the uranium. We know the in the nature there are two isotopes available in nature, that is uranium-235 and uranium-238. So among these two isotopes, the uranium-235 can do spontaneous fission, but the percentage of uranium-235 in natural uranium, it is only less than 1%, 0.72%. So definitely it is to be enriched. The density of the percentage of uranium-235 is to be increased when it will be used in nuclear power generation. So normally in nuclear fuel pin, where the nuclear reactor is used for power generation, so there the enrichment of uranium-235 is needed around 3.5% or 4 to 5% also, and for nuclear weapons it is needed 90%. So to do this, centrifuge is used extensively. So I will, as I told, I will add a few slides about the this uranium when it is taken from the mine and how it is post-processed. So normally, once the uranium is taken from the mine, so there itself, it is that uranium is to be oxidized and it is converted to yellow cake, which is nothing but the uranium oxide. Then the fluorination will be done on the yellow cake, and this yellow cake will be converted to uranium hexafluoride gas. So as I told, then the uranium hexafluoride will be containing two molecules. One is uranium-235 hexafluoride and uranium-238 hexafluoride. So then this, using this centrifuge or some mechanical process, you have to increase the concentration of this hexafluoride, and after that again it is to be converted to uranium. Okay, so there are several techniques. So one very easiest technique is, as it's this uranium-238, it is slightly higher, the size, the volume of the molecule is slightly higher, and uranium-235 molecule is comparatively lower in size. So if these two mixture, because the natural uranium contain these two isotopes, so in the same percentage the hexafluoride also it will be formed, and once you pass this mixture with a high pressure in a chamber which is separated by a porous membrane. So this is the membrane. So due to the pressure, normally the molecule which are of lower size, it will pass this porous membrane. So the gas, the hexafluoride, which will be collecting from this port, so there the concentration of uranium 235 hexafluoride will be higher than this port. Okay, so this is a very simple mechanical procedure. Another procedure is, this is the very efficient and nowadays it is used, that is called centrifuge. So centrifuge is nothing but it's a rotating container or chamber, so where these two hexafluoride mixtures are fed through this pipe or the inlet, and then this container is rotated with a very high speed. So, and due to the centrifugal force, and this centrifuge is used, so normally this say there is a mixture of mud, there is a muddy water. So if you keep it for a long time, due to gravitation itself, this sedimentation will take place, and you can take the mud will be separated out. So here the density difference of the mixtures are more. So you can use the gravitational centrifugation. But where the density difference of the mixtures are very less, or the density of the mixtures are very near, so that time this gravitational centrifugation, it will take much more time, and the separation will be not that much perfect. Okay, so in that case, this where the density difference of the mixtures are very less, so there the centrifuge are used, where the container will be rotated at very high speed, and due to centrifugal force, the particle of higher density, it will be accumulated in the outer layer of the container, whereas the particle of lower density, it will be near to the axis of rotation. So in this case, through this port you can take out the uranium 238 hexafluoride, and through this port you can take uranium 235 hexafluoride. Okay, so this is done in uranium processing or enrichment. This is done in several cascaded state. So maybe there will be 100, 500, thousands of centrifuges will be used to separate out the mixture. Okay, so this is the practical picture, where you see there will be a series of centrifuged, and it is a cascaded together. So the after the separation from one stage, it is going to successive stage, and we are continuing this cascaded series till we are getting the desired enrichment of the uranium. So this is once again slightly it is detailed more using the chemical equations. So first, this water or some alkaline or other oxidizing solution are applied in while it is in the mine itself, uranium mine itself, and it is converted to uranium oxide, which is called yellow cake. So basically the yellow cake are nothing but the U3O8. Okay, after taking this yellow cake, it is dissolved in nitric acid, okay, and which convert this uranium oxide to uranyl nitrate, that is UO2 NO3 whole 2. Then it is treated with ammonia, and this urinary nitrate is converted to ammonium diurenate, which is NH4(2)U2O7. Then the reduction is done, okay, and this will be converted to uranium dioxide. Then the uranium dioxide is reacted with hydrofluoric acid, okay, and this uranium dioxide will be converted to uranium tetrafluoride. Then the fluorination will be done on that uranium tetrafluoride, and you will get the uranium hexafluoride. Some people, the one country, they will use their own technique based on their capability and convenience, and somewhere some people, they will directly, the uranium will be reacted with the chlorine trifluoride, and directly it will give uranium hexafluoride, and it will release some chlorine also. So one in USA, one famous uranium processing facility is this called the Honeywell uranium hexafluoride processing facility. So here you see, this is the yellow cake. It is reacted with hydrogen, and it will generate uranium dioxide. Then this uranium dioxide, it will be reacted with hydrogen fluoride or hydrofluoric acid, and this uranium dioxide, it will be converted to uranium tetrafluoride, which is called green salt. Then the fluorination will be done on this uranium tetrafluoride. The fluorine will be added with this, and this uranium tetrafluoride, it will be converted to uranium hexafluoride. So this is the simple process, that how from the mine the uranium will be converted to uranium hexafluoride. So this uranium hexafluoride will be containing two molecules. One is, because the uranium having two isotopes, so this will be uranium 235 hexafluoride and uranium 238 hexafluoride. Their density difference will be very less. So the other type of centrifugation, it will not be that much efficient, so we will be using the centrifuge. So before going to the centrifuge, the basics, I will show one video. So you see here, this is one muddy water. It is poured in the tube. Then there is outer casing to hold in the manual. This is the manual centrifuge. The RPM is, this is the lime water. So the mixture is very uniform, and if you use the gravitational centrifugation, it will take much more time. So just it is one centrifuge. It is used to separate very quickly. So the equilibrium, it will come very quickly. Now it is rotated. It is rotated for some time with some higher speed. So there are some gear arrangement is there, which is it's a type of worm gear. So it is rotating very high speed. It is getting rotated. Now you see, once the tube is taken out, you see how quickly the muds are sedimented at the bottom. Very quickly, within a minute time. You see the calcium oxide, those also, it is very quickly, it is sedimented. So this is basically the fundamental behind the centrifugation. So now coming to the very fundamental theory of it. Say this is a container. This is a container. So this is the axis of rotation. So this axis is rotating with a speed of, angular speed of omega. Okay, angular speed of omega. So there is a annular path where the liquids are kept, and the distance from the inner wall of this annular area is R1, and the radius, the distance from the axis of rotation to the outer wall is R2. If it is like that and the height of this is B, then if you consider the from the axis there is a distance R, and there you are taken one small strip of liquid dr, and we want to find what will be the pressure distribution inside the liquid. So normally the centrifugal force, we know that will be m omega square r. So this is the small mass, which is nothing but the mass of this liquid stream. So mass basically the volume into the density. So this is the density, and 2 pi r, this is the entire, it is a cylindrical, so this is circular periphery, so that's a 2 pi r into b, it is the height, and width is dr. So this is the volume and this is the density, so it is mass. So now if we want to find out the pressure, then the pressure is nothing but the force divided by the cross section. So cross section in this case, it is say that there is a cylinder. If you cut, it will become a rectangular shape. So this length will be 2 pi r, and the breadth is here b. So if you divide by this, so this term is converted in this form. So now if you integrate to get the pressure, so we have to integrate it because we want to get the pressure distribution here inside the liquid. So this is, we have to integrate from R1 to R2. So the pressure difference in this liquid in the inner and the outer wall, it will be half rho omega square R2 square minus R1 square. Okay. So in a centrifuge, this is basically the pressure difference, and using this we will find out the equilibrium. Now consider basically the construction of the centrifuge is like this. So there is a feed through which the liquids, the mixture of the liquids are poured inside, and there are two ports. See, this is one port, port 1 and port 2. It is rotating at, say, speed of, this entire centrifuge is rotating at speed omega. This omega should be very high, nearly above 5,000 to 10-15,000 also. So how much should be the speed, that all these things you have to decide based on the how much efficiency you need and what liquids are to be separated. All these things are further detailed mathematics and technology development, so that I am not discussing in this lecture. I am giving you the very basic of it. So after once this, so naturally the liquid of higher density will be collected through port 1, because due to once it is rotating at high angular speed, so this will be going away from the axis of rotation, and comparatively the liquid of lower density, it will be accumulated in the inner wall, near to the inner wall of the centrifuge, and at equilibrium there is a layer will be formed which will be separating both the liquids. So say that distance is the at equilibrium, after some time, once you are rotating at a very high angular speed, so this layer, the distance of the layer from the axis of rotation is Ri, and the port A distance is Ra, and port B, where the liquid of lower density will be connected, that is Rb. So from the earlier equation we understood that what will be the pressure distribution. So this will be this at the equilibrium. So the pressure distribution, the pressure difference between these two and the pressure difference between these two layer or these two wall, it will be equal. Then only it will, that equilibrium state will reach. So already we learned the formula. So this formula is written. So this is for the liquid B, rho, that density is this one, and omega, this is the angular speed, and for the liquid A it will be this one. And from there, if you simplify, then you can find out where the at equilibrium, where the so what we were discussing. So at equilibrium, where the how the separation, at which position the separation will be taking place, so that we can calculate using this formula. Okay, and for efficient use, these ports are made, the collecting ports are made such a way that the distance it can be moved, means the distance RA and RB can be varied. So why it is required, we will understand using a very simple example. So let us take one example, that a centrifuge is rotating at 8000 rpm and the diameter is 250 mm. So that means from this center it is 125. Okay, it is used to separate water from chlorobenzene. The water density is 1 gram per cc and the specific gravity of chlorobenzene is 1.1, slightly higher than water. And the heavy liquid port, that means this RA is here 50 mm, and the lighter liquid port, it is RB, which is 40 mm. Okay, now we have to find out the position of interface. After once the equilibrium is established, then where the two liquids are interfaced. So simple, if we understood the equation, if you put it, so it is 108 mm. So that means this distance is 108. So this distance is 108 minus, sorry, 125 minus 108, it is 17 mm. Now you see this thickness in this example, it is very less, only 17 mm. But if the concentration of liquid A, it is the volumetric ratio is much more, then it may not be possible to accommodate. So this equilibrium will not take place properly. Okay, or it will be that it will take it will be difficult to separate it out. Okay, so for that what is to be done? In such case, this Ri is to be reduced. So if you want to reduce it, because here rho A, rho B, all are constant. So either if you want to reduce it, either you have to increase the RB, or you have to increase or you have to reduce the RA. That time you see you need to vary the port distance from the axis of rotation. So here if this RA is decreased from 50 to 45, then this RI will reduce to 180. So if it is reduced to sorry, it will be reduced to 80. So if it is reduced to 80, then this distance will increase to 45 mm. So that time you can, the more liquid can accumulate. So it is a very simple calculation. If you are able to know the volumetric ratio, then where the interface is taking place, so based on that you can find out whether it is sufficient to accumulate there or not. If it is, if your volume is after calculating the position of interface, if that volume is lower than that volumetric ratio of the liquid, then definitely it is to be altered. And all these things you have to do based on your mixture and the density and all other parameters. Now the second question is how to know that the equilibrium state is reached. So that is predicted, which is called centrifugation time or pelleting time or pelleting efficiency. That is determined by, it is a experimental method to establish that. So this is defined by a formula called K factor or the pelleting efficiency. So this is empirically it is expressed as this: K is equal to natural logarithm of R max by R min into 2.533 into 10 to the power 11 by n square, where n is the RPM of the rotor and R max is, which one R max? So in this case R max is this one, and what is R min? This is R min. Okay, so you can find out. So this, it is a common sense that if the density difference is more of the mixture, the two mixtures having the wide density difference, then at very less RPM and very quickly you can get the equilibrium. So first, to find out the K factor for a given liquid, you take the centrifuge and you rotate it as a at a known RPM, and by this formula you calculate this R max in the previous, based on the previous slide. You can find out the R max and R min, then you can find out the K factor. Okay, and by experimental method you can find out what time it will take to reach the equilibrium for that particular known density mixtures, okay, which having wide density difference. So for that the K is K1 and the time taken for equilibrium is T1. Now you consider the liquid which having very less density difference. So for that numerical method means analytically you can find out this R max and R min, so you can find out the K2. So your T1 is known, K1 is known and K2 is known. Now you can find out the T2. So this is the method to, so this is basically, I will show the slides once again. So this is the, basically this is the physics behind a centrifugal separation method, and during equilibrium how the pressure is distributed inside the liquid, and this is the expression to find out the position of the, or the layer of separation of the liquids at equilibrium. And you know, this is the one example I have given to find to explain how to find out the position of interface of the liquid at equilibrium. and sometime it's not whatever analytically you calculated, that may not be feasible or appropriate based on the volumetric percentage of the liquid. So that time you need to change it. So that time you need to, basically the parameter which can be varied, that is your port distance from the axis of rotation, and how it is to be done, because this position of interface, it is independent of omega. Okay, so this omega is responsible, so this is omega will depend, it will be responsible to determine the efficiency, the pelleting efficiency, as well as the equilibrium, how quick the equilibrium is reached. So to find out the centrifugation time, you need to first find out the K factor and the equilibrium time with a liquid of which with a mixture of liquids, their density difference is very high. So very quickly you can achieve the equilibrium, and that is say K1 and T1. Now you take the mixture of liquid whose densities are very closer, and from there you find out the K2, and if you put those values in this formula, then you will obtain the T2. That much time you rotate the centrifuge, you will achieve the equilibrium. So this is the very basics of centrifuge, but you may think that it is very easy, but the design is very tricky, because you know the RPM, the rotation, the prime mover, the motor should be designed for very high RPM. Nowadays BLDC motor and all these things came, so this you need one inverter. So that inverter, the power frequency of the inverter should be very high, and it is to be switched at very high frequency. So that time, once the inverter is operating at very high frequency, so eventually it will increase the conduction and the switching losses. So that is to be evacuated. So there is a huge your convective heat transfer coefficient, or the heat sink design should be sufficient enough to evacuate the heat produced from conduction and the switching loss of the semiconductor device. You have to maintain the power quality. All these things are during design, it is to be taken into consideration. Then the bearing design, it's a very difficult task to select the dynamic capacity and the material, the material of selection. It will be very difficult to design. Again, it goes to material science. Then the construction of the rotor, its machining, the tolerance, the dynamic balancing. You have to use the highest grade of dynamic balancing. Otherwise, it will if there is any residual mass, you know, any residual mass in the rotor dynamics can cause the unwanted vibration. Your critical frequency of rotation. So many technical things are there which are to be considered. So I have given you a very basic idea about a centrifuge. So hope it will be useful to you. My contact details, it will be given in my given in the video description. You can write me in case of any further or specific queries. I will be happy to discuss with you. So thank you so much. Thanks for your patience.